Hi, I want to talk about black holes. So under a classical understanding of physics, black holes are explained using the idea of energy conservation and escape speed. In order for an object to leave the gravitational potential created by any mass, there's a minimum speed that that object needs to achieve in order to get infinitely far away, what we call the escape speed. And for any gravitational object in classical physics, the escape speed is the square root of 2 times the universal gravitational constant times the mass of our object divided by the radius of our object, assuming that it's spherical and uniformly distributed. Well, for light, it travels at a fixed speed, the speed of light. And we know now that the speed of light is something that is absolute. Light can't exceed it. Light can't go any slower than it. Light travels at that speed always. So, if an object were to need to travel faster than the speed of light, it wouldn't be able to escape. So, light wouldn't be able to escape a black hole. So, we can rearrange this to solve for what radius our black hole would need to have. So if I square both sides, I'd have the speed of light squared is 2 times the strength of gravity times the mass of our object divided by its radius. You can multiply both sides by the radius and divide by the speed of light squared, and we get the formula for what we call the Schwarzschild radius of a black hole. The radius would be 2 times the universal gravitational constant times the mass divided by the speed of light squared. So, say we wanted to make a black hole, but we wanted to use the amount of mass that we have in planet Earth. Now, planet Earth can't collapse into a black hole. Our sun isn't massive enough to collapse into a black hole. But when the universe was formed, there might still be some leftover black holes that have masses around the size of masses of the planets or masses of some of our planet's moons. So for something that was Earth mass, well, Earth's mass is 5.98 times 10 to the 24 kilograms. We plug in our values. Again, the universal gravitational constant, 6.67 times 10 to the negative 11. Newtons times meters squared over kilograms squared. Mass of Earth divided by the speed of light squared, 3 times 10 to the 8 meters per second is plenty precise enough for this. And this is the big thing to watch out for. It's really common with gravity problems to forget to square things that are squared, or if something needs a square root or a cube root, forgetting to take those powers. Watch out for the powers. So, plugging in everything, we end up with a radius of 0.00886 meters. Or, imagine shrinking Earth down to something smaller than my fingertip. That's how large an Earth-sized black hole would be. Thanks for watching.